session. Our first speaker is Professor T. Padmanabhan of the IUCA at Pune. He is a distinguished professor and dean of core academic programs at the Inter-University Center for Astronomy and Astrophysics at Pune. His research interests focus mainly on the structure formation in the universe, on the interface between gravity and quantum theory. He's written several books and is a recipient of several honors and awards, including the Padma Shri. That's what the official statement says here in this little description. I should also mention that in passing, maybe, that over and above this, which doesn't really do justice to all of Paddy's achievements, he is one of the world's leading astrophysicists and indeed theoretical physicists. And I should also mention, especially for the students, the very great interest that he has in pedagogy, in teaching, and the very large number of articles that he's written in places like Resonance, in which he continues to write. It's, I've tried to make inquiries as to what his work habits are like, and the only piece of information that I could get with some reliability was that he works till 3 in the morning and then wakes up early in the morning and starts again. So it's not clear to me when he gets his rest, but I guess working at that pace is what keeps him going. Paddy is going to speak today about what does classical gravity tell us about the quantum structure of space-time. You have 55 minutes, and would you care last 3 minutes for questions? Paddy.
Let me begin by thanking the organizers for inviting me to give this talk and for the nice introduction from Balki. I don't do anything of that kind. I go to sleep at 2, but I get up conveniently at 9. So this belongs to the category of talks in this conference which doesn't have anything directly to do with Chandra, and I have given a highly Chandra-centric talk in a different conference, so I have paid homage to the great man. And also I had often wondered if Chandra had lived for 2 more decades, what is the next topic he would have taken up? And carrying forward from black holes and gravity and statistical mechanics, probably he would have gone to this area. It's just that he died a little too young. Okay. So the title of the talk is, what does classical gravity tell us about quantum structure of space-time? And a strict logician will say nothing. After all, classical gravity has no H cross and quantum structure presumably has a H cross. So we won't be strict logicians, we will be physicists, and you will see in which way this is to be interpreted. So the paradigm which you should keep in mind for this entire talk is that gravity is an emergent phenomenon like elasticity or fluid mechanics. Fluid mechanics has its own variables. You can write down self-consistent set of equations and solve them and use them in many practical contexts. But we know that that is not the whole story. There is a microstructure made of molecules or atoms, and this comes out in some long wavelength limit of this. So this is what one wants to do. At this level of statement, it is sufficiently vague that nobody can disagree with it. And if you talk to someone who is actually doing quantum gravity, string theories, or loop quantum gravity, or dynamical triangulation, or whatever, they will all say there is some microstructure to space-time, and gravity is the long wavelength, the classical gravity is the long wavelength phenomenon. What really distinguishes my approach, which I am going to present today, is that I am going to claim and convince you that there is sufficient amount of internal evidence in the structure of classical gravitational theory itself for this. So from top down, if you look at it, you will be able to see some of these signatures, which I will try to describe. Now this has a very long history. The basic approach, that is an emergent phenomena, has a long history. It started with Sakharov. Various people have tried to implement it in very many different ways, etc. But in this talk, I am only going to cover my work and the work of my collaborators. And the distinguishing point between all these work compared to what I am going to talk about is this line, that I am going to concentrate on this internal evidence which can be deciphered from a top-down approach. Now let me begin by just asking whether the top-down view will ever help. This is like knowing root pi and guessing that the integrand is e to the minus x square. I mean, obviously you cannot do that sort of a thing. So when will it work? It will work provided you ask the right questions. So before we proceed to the topic itself, I wanted to describe to you at least 2 examples which you all know but probably has not viewed in this way. When does Okay, first of all, by top down I mean going from large spatial scales to small spatial scale. At least in one conference, particle physics got confused because they thought of it as top down in energy scale, which is of course different. So you are going from classical to quantum. So let me give you two examples where this has worked out. The first is you look at a gaseous system as Boltzmann did, and the gas exhibits thermal phenomena. It can store energy, it can exchange energy. And all these can be described in some continuum mechanics, but you can never understand how a gas can have thermal energy in the continuum limit. If a gas is continuous all the way down to infinity, it cannot store thermal energy. And the explanation for this comes from atomic nature of matter. So just staring at it, you can say that the heat is a kind of a motion of microscopic degrees of freedom. There is also an important relation which we will keep coming back to, which tells you that if you have the system with some energy at some temperature except for some numerical factors, this variable and this variable are purely thermodynamic and they are well defined in the continuum limit. But this quantity has no meaning in the continuum limit. It actually counts the number of discrete degrees of freedom which is there in the system. So this equipartition law has a very direct connection, starting from variables on one side which are continuum, telling you about the microstructure on the other side. Okay, let us keep that in mind. The second and more dramatic example is the question, why is inertial mass equal to gravitational mass? This is a question which can be posed at the level of classical Newtonian gravity, and it has been known for ages. Now you ask for an explanation, and this is the coarse-grained theory or the approximate theory, and the theory already contains a clue as to the really underlying theory, which is the geometrical way of looking at gravity, which allows you to interpret this result in the most natural fashion. It embeds this result in a scenario which makes it very natural. So here are the two examples in which you can add more examples. Top-down view really did help. But the moral is that if this has to help, you need a very strong gating principle, like principle of equivalence, in order to make progress. So what is the equivalent principle in this context? I would like to argue that the equivalent principle which we have to use in this context in order to make progress from macroscopic theory of classical gravity to the quantum structure of space-time is the fascinating relationship which we know between the horizon thermodynamics and gravitational dynamics. This must be at the foundation. So let me try to explain a few more things related to this. Once you accept this, there are also a few additional ingredients you have to keep in mind in this approach. The first is the general feeling which I have, and shared by some people at least, that combining GR and quantum theory is not a technical issue, but there are some conceptual breakthroughs which is sort of awaiting to be discovered. The second, which is somewhat more technical, is that there is a distinction to be made between what I would call the quantum structure of space-time and quantum gravity. So let me explain what I mean by that. Suppose you have elasticity, which is like the classical space-time in my analogy, and you go and quantize elasticity, the equations of elasticity. You will get phonons, but you are not going to get atomic structure of matter. In the same sort of way, if you take a classical theory of gravity and you quantize it, you will get gravitons or some such description. But that may not be exactly the same as the quantum structure of space-time. You may have to probe deeper. So there is a distinction between these two. Third, in this particular approach, if you are coming bottom up, suppose you believe in loop quantum gravity and you are working on it, or you believe in string theory and you are working on that, then you have a lot of strength in your hand and you can explore its consequences. But since I am doing a top-down view, I need to think more holistically, and the black hole horizons for me is just, black holes for me is just an on-shell solution to a classical gravitational equations. And their horizon and thermodynamics, however fascinating it is, cannot be the whole story. One needs to think well beyond black hole horizon. It also turns out that for technical reasons, you need to think well beyond Einstein's field equations. You want to look at a wider class of theories of gravity. So all these ingredients go into this, and this is what I wanted to explain in the form of a series of internal evidence in classical gravitational theories for the quantum structure of space-time. Okay, so here is the plan of the talk. I'll first describe the conventional approach to gravity and horizon thermodynamics, because all of you may not be familiar with horizon thermodynamics. then the key point of the talk would be this internal evidence for an alternative perspective. And just as you have E is equal to half n kBt, I will get you something analogous to the Avogadro number of the space-time, which tells you how many microscopic degrees of freedom are there. This we will derive. And then I wanted to talk a little bit more on what this implies for a bottom-up scenario possibly. Okay. So let me begin with the most elementary statement of the relationship between horizon thermodynamics and horizons and their temperature. Space-times, like matter, can be hot. You take a material, you heat it up, and its temperature can change. So if you have an observer who perceives a horizon, then he will attribute to that horizon a temperature. In fact, any null surface which acts as a horizon for him, where this is the acceleration of the observer or the surface gravity of the horizon depending on the context, and this is the only place where you will find all the fundamental constants. So the classic example which we know is the black hole space-time. This is time, this is space, and this is the 45-degree line is the horizon. The coordinates are chosen so that light rays are 45 degrees. An observer who is sitting quietly at some radius will follow this hyperbolic trajectory, and he will attribute to this horizon a temperature which is like this. Another observer who is freely falling into the horizon will say there is no such temperature. So the horizon thermodynamics is an observer dependent effect. Here in this case, the observer at rest or similar class of observers will see this. Same thing happens in flat space-time. So here is a flat space-time, and there is an observer who is shooting off in an accelerated rocket. His trajectory happens to be this, and he will attribute to this horizon a temperature which is proportional to his acceleration. In fact, a more general statement can be made with some very well controlled approximations, that if you have a freely falling observer and have an inertial coordinate system around some event with light rays going 45 degrees, in that local region if there is another observer who is accelerating, then the vacuum state of this observer will appear as a thermal state of the other observer. Now, at least for those who are sort of familiar with this to some extent, I wanted to give you a one transparency derivation of this result, mainly because it is extraordinarily cute. Let me do it in the context of Rendler frame. This is flat space-time but in Euclidean coordinates. So this is the Euclidean time and this is the real space. Now you take polar coordinates in this plane. So in the polar coordinates, this particular angle corresponds to the Rendler time coordinate, the time coordinate of the accelerated observer, and this corresponds to the radial coordinate of the Rendler observer. Now there is a well-known formula in quantum field theory or quantum mechanics that the vacuum state can be expressed as a path integral of a Euclidean action with the appropriate boundary condition. So you are evaluating the path integral in the upper half plane, giving a boundary condition here that the field should have some phi L and phi R here, and you are doing the path integral all over. Now the path integral can be time sliced along these lines, or it can be time sliced along these lines. You just write both of them and equate to each other. If you do the time slicing from here, you start attributing this boundary, and then over this evolution, so to speak, you attribute this boundary condition. This is what it will look. And this, of course, has the standard Heisenberg picture representation, which is this. So the final result is that the vacuum functional can be expressed in this form, where HR is the Hamiltonian, which allows time translation in this. That's all you need. Now you trace out all the modes which you are not observing, the phi L, and you get a density matrix, and you just do the d phi L of this quantity. An elementary calculation here will give you that this will become 2 pi because you multiply twice, and this is what you get. This is a thermal density matrix with a temperature equals to 2 pi over kappa. So you can immediately find that without ever saying anything about the field equations of the theory, you can attribute in a wide class of scenarios a temperature to a null surface or to a horizon. It is very important to realize that this has nothing to do with the dynamics of gravity. You give me any metric which has an appropriate null surface and an appropriate observers, I will attribute to it a temperature which knows nothing about the field equations from which the metric came out. Okay. This is devoid of dynamical content. And as I said, it just shows material can be I hope it doesn't come up again. Now, given a thermal density matrix, there is a very natural entropy associated with it. And you can say whether the horizon has an entropy. And you try to calculate it, and you find it is divergent and therefore meaningless. So the quantum field theory in curved spacetime can give you temperature of the horizon, but it cannot give you the entropy from the quantum field theory treated as a test field, etc. Now, there is a reason for that. The reason has to do with the fact that the entropy of a horizon depends on the field equations of the theory and the kind of gravitational theory which you have. So you need to go and look at how gravity is described. So again, one transparency summary of theories of gravity. So there are several excellent textbooks in the market. You go and pick something at random and you look at how theory is developed. So it starts with the principle of equivalence. Then it tells you the general covariance. That is not sufficiently discriminative. You need an action functional to describe the dynamics. So one class of action functionals which is adequate for our purpose is an action functional where the gravitational action depends on the Riemann tensor and the metric. Now, if you vary this, you will find that the equations of motion has this form, which involves up to fourth derivatives of the metric. Okay, where this P, A, B, C, D, which is going to play a crucial role in what I am going to talk about, is the derivative of this with respect to the Riemann-Christoffel tensor. For reasons which will become obvious, I will call this the entropy tensor of the theory. So you have this. But then you can say that, look, I want a nice class of theories where the equations of motion are up to second order. Then you want to impose the condition that the divergence of this already has all the algebraic symmetries of Riemann tensor. You in addition impose the conditions that its divergence should be 0. This problem has been completely solved. I mean, people know what is the most general tensor which satisfies these conditions. This is called Lancos Lovelock tensor. And the equations of motion which results from it defines for you what is known as Lancos Lovelock theories. I will just call it Lovelock theories. In all these theories, horizons arise quite inevitably, and we want to look at the entropy of these horizons. So, of course, in Einstein's theory, the whole idea was that you have a hot cup of tea here, and if you sort of tuck it into this, John Wheeler was worried about the fact that the entropy can be lost to the outside world. And Bekenstein pointed out that in that process, the area of the black hole will increase, and you can attribute an entropy which is proportional to the area. What I want to emphasize is that this proportionality between entropy and area is a very, very special feature of Einstein's theory. In all other theories, the entropy is given by a much more complicated formula, and they are as natural as Einstein's theory. The way it comes about in another theories is rather strange, so let me describe that. All the other theories are invariant under this diffeomorphism, and that leads to a Noether current and a Noether potential. So you first find out what the Noether potential is, then you do an integral, you essentially compute the Noether charge, and you already know the temperature of the horizon, which has nothing to do with the theory. And if you do the math, you find that it is essentially an integral of this tensor, which I told you completely describes the theory. Okay? This tensor integrated, this is just a binomial on the surface, integrated over the horizon, gives you the entropy of the theory. So in some sense, the variation, first variation of the entropy with respect to the binomial will tell you what the theory is about. So the entropy knows about the space-time dynamics, while temperature does not. Need not surprise any condensed matter physics. If I give you a material body and I give you the entropy as a function of E and V, I know the thermodynamics of the system and I can do the dynamics, but I can keep this material body at any temperature I like. So temperature contains much less information, just a parameter, while the entropy knows about the space-time dynamics. However, the connection between this and entropy is a complete mystery in conventional approach. Those who know elasticity should think of this as an elastic deformation of the space-time solid, and the entropy which is coming out is, at least in my approach, is going to be related to that. Okay, so far this is the overview of the conventional gravitational theories, and now I wanted to go and ask, what about the alternate prescription? So the first question is, why do I want to do that? And I want to convince you that there is a whole lot of algebraic accidents which needs explanation in this model, and they provide the internal evidence that we are looking at the gravity the wrong way around. This is exactly like the fact that if you have m inertial equals m gravitational, it requires an explanation is what you need to realize, and then you try to come up with a formalism in which it is naturally embedded. So let me give you the first example. You take a spherically symmetric space-time with a horizon at r is equal to a. I am talking about Einstein's theory now, and it has a surface gravity g. Then I already know I can attribute this temperature to that. Okay, this has no dynamical content. Now you go and look at the dynamics. You write down Einstein's equation at the horizon, r is equal to a. And this is the equation you will get, where P is the pressure of the external source which is producing it. Just if there is no external pressure in the external source, you put it to 0. So let us write this down. You may not think this equation looks like anything which you have seen in thermodynamics. All you have to do is to multiply it by dA, and then you can rewrite that equation in this form. So the right hand side is P dV, what is known as areal volume. This is already temperature, and I put in by hand a h cross at the top and the bottom in order to make that identification. Then you can immediately read off these two, and you find that the Einstein's equation reduces to a thermodynamic identity on the horizon, from which I can uniquely read off the entropy, which is 1/4 of the area, and the energy, which is essentially, if you take short sail, it is a by 2, which is 2m by 2, which is m, just out of this. Okay. And there are all sorts of things about whether how it is unique, whether there are things which you can do, and this is all described in an early paper I wrote in 2002. This is fine, and this is very tantalizing, but you might just say that, well, this may be a curious thing which happens in Einstein's theory in a spherically symmetric static horizon or whatever. After I did this work, several groups have tried to generalize it, and in the last 8 years or so, there is a whole lot of cases where this has been looked at. In all these situations, many of which much more general than Einstein's theory, gravitational field equations reduces to a thermodynamic identity of this form, with exactly this form, with the correct entropy being picked up at every time. The entropy is not proportional to area in many of these cases, and a very complicated expression for entropy, the Wald entropy, will be picked up. And in all these cases, the gravitational field equations of a diffeomorphism invariant theory reduces to a thermodynamic identity on the horizon of the theory. Now, if this is really true and the gravitational dynamics has this alternate description, shouldn't the action functional itself contain a hint of it? Because after all, it's the action functional from which we derive the dynamics in the conventional approach. And in fact, it does, and I wanted to talk to you about that. Einstein's gravity, or in fact, a class of gravitational theories, is the only thing which we know in which the most natural action you write will have a surface term. For example, in Einstein's theory, you can separate it into a bulk and surface term, and there is a bulk and there is some divergence here, which can be integrated in order to give you a surface term. Now, what is interesting is that usually you throw away this term either by a formal cancellation of the variation or just ignoring it, and you vary the bulk term. So the theory knows nothing about this surface term. You have thrown it away at chapter 1. Then you vary this bulk term, you get field equations. Let us say the field equations, you take one solution with horizon to the field equation, like a black hole's horizon. Okay? We have checked this out. Now you go and evaluate this surface term just for fun on the horizon, and you find that it gives you the entropy. Now that is very strange. How does the surface term which you threw away know about the dynamics and the physics determined by this bulk term? Okay? Now there is a reason for that. The reason, in some sense, I call it holography, not in the way string theorists use that term. It's a little known fact that if you have a classical mechanics 101 kind of an action with q and q dot, with delta q equals 0 giving you the field equation, I can write down another Lagrangian which has q, q dot and q double dot dependence, but still gives you exactly the same equations of motion, provided I construct this LP by taking this LQ and doing a minus d by dt of this. I mean, if you think in terms of canonical transformations, it is rather obvious, but you can do this entirely in the Lagrangian picture. Okay? So these are a class of very special class of Lagrangians which involve second derivatives of the dynamical variable. They are structured in a very special way. It turns out that Einstein gravity on the whole wide class of gravitational actions, all the gravitational actions I told you, has precisely this structure. The surface term is not something arbitrary. It is related to this like a q, and this is the p of the system. So as a result of which, there is an information duplication between L bulk and L surface. Under some reasonable assumptions, you can construct one out of the other. So they sort of share the information, and that is how the surface term gives you the entropy. In fact, if you look at the Euclidean action in any static spacetime with a horizon and a temperature, it turns out that the bulk term is beta E and the surface term is S, the entropy. So the whole thing can be thought of as the free energy. The action itself, or the Lagrangian itself, can even be expressed entirely in terms of the Noether potential. And I told you that the divergence of this Noether potential gives you the Noether current, and it is this Noether current's integral which gives you the entropy. So this is the surface term. So this is an identity, and the bulk term can be related to the energy. So the gravitational action, the standard gravitational action, also has a thermodynamic interpretation. So the question is, you can give more examples of this, but the question is, how does this work? Why is there a thermodynamical interpretation? Now this is very natural if you say that gravity is an emergent phenomena. So let us go back and look at the gaseous dynamics for a minute and try to draw up the analogies. So the basic dictum of Boltzmann was that if you can heat something, it must have microstructure. If it is not there, it cannot store that extra energy, and you cannot do that. So in the standard description of any system which is interacting with mechanical systems, you have these two kind of degrees of freedom, and the Boltzmann's genius was to sort of say that they are one and the same, and it is the mechanical variables of the microscopic degrees of freedom which you call thermodynamical. But there is a new key ingredient I alluded to in the very first thing, which is the equipartition law. You can actually take, let me use this version because I need to get the scalings also interestingly. You can write the energy of a system. If you think of a system with a slowly varying temperature or something, dN by dV is the number of degrees of freedom per unit volume having a temperature T. So then the equipartition tells you that you can write this law. So this relates to thermodynamic variables with the granularity of the system. Now if I go from the gaseous dynamics to the space-time and say that you can heat up a space-time, so it should have microstructure, then it suggests that we study space-time exactly the way physicists studied gas dynamics before they understood the atomic structure of matter. So the thermodynamic description should have the same pros and cons. For example, it would be independent of the exact microscopic quantum gravitational interpretation. And many of the variables which we use like metric curvature will have only a meaning in the macroscopic limit. The entropy has to be related to the degrees of freedom which you are coarse graining over. But then there is a crucial test to this idea. In the case of gas dynamics, people could actually measure the Avogadro's number even before they knew what it is counting. So in the same sort of way, if space-time has some microstructure and it can be heated up, is there an equipartition law? Can I ask how many degrees of freedom I need to store an energy E at a temperature T? Because E and T I can define, can I get my N? Remarkably enough, you can do that. So this is what I wanted to explain to you. It turns out that classical Einstein's equations can be written in this form. You can write it in any spacetime which has this temperature, the acceleration temperature. The energy, the gravitating energy, which is technically known as the Komar energy, can be thought of as an integral over the surface, the bounding surface, times the acceleration temperature, so that it has exactly this form with two crucial features. First is this temperature, of course, is the acceleration temperature. This is an identity which comes from the field equations. What is important is that it scales as the area. The number of degrees of freedom which is contributing is residing on the surface of the thing, and that is why I call it again gravity is holographic. And we saw that in the case of normal gaseous systems, it would have scaled as volume. And the number of bits which you have, the number of degrees of freedom is 1 per Planck area, which is exactly what you would have normally expected in Einstein gravity. But what is remarkable is that this result generalizes to all diffeomorphism invariant theories of gravity. For example, in the Lovelock model, the same result holds. The only difference is that here the dN by dA was just a constant. Per unit area there was 1 over LP square. Here dN by dA is given by this entropy tensor, which is exactly what you would expect, because the entropy is going to scale with this dN, and that should have this information about that. So the way the degrees of freedom are distributed gives you information about the theory, and it holds for every theory. So I will skip this because maybe I can spend some time. Okay, so I want to illustrate this for those who are not in this field in a very simple example. You consider a black hole, and there is a temperature here due to this acceleration of this observer who is sitting there, and the whole space-time is now hot. Now what you do is you attribute the kT, the acceleration goes as gm by r square, and then you take the number of degrees of freedom there, which scales as r square. So it's just Gauss law. So if you take half n kT, the n which scales as r square and the kT which scales as 1 over r square will all nicely cancel out, and you will get this result E equals mc square. Okay. So this is a very simple context. Of course, this is like 1 by r square acceleration and all that. In spherically symmetric cases, everything works out. Okay. But as I said, the result is much more general than that. So what does this imply for you? Roughly speaking, this is what is happening. Let us try to do a comparison between a macroscopic body and space-time. So you ask, can the system be hot? The answer is yes for both. Now can it transfer heat? Yes, a hot gas can be used to heat up water. And yes, the answer is yes in space-time also. If you take a glass of water and you run with an acceleration, you can prove that the water will get heated in the inertial vacuum. So this is just the Unruh effect. Now how does this system or the space-time store this energy? Then Boltzmann told us that there must be microscopic degrees of freedom. Space-time should have microscopic degrees of freedom. Up to this point nobody would disagree, but the really concrete thing which I want to stress is that you can make some quantitative statements about it. You ask how many degrees of freedom you need to store an energy dE at temperature T. The answer is dN equal dE upon half kB kT. Don't take half too seriously, but dE upon T essentially. Same thing here. So can we read off this dN? Yes, when there is thermal equilibrium, depends on the body here. And when static field equations hold, and it depends on the theory of gravity which you have. It encodes the same information content as the theory of gravity, as it should, because the degrees of freedom, microscopic degrees of freedom, when coarse grained, gives you that classical gravitational theory. So what would be the expression for entropy? That should scale as this delta n, that will scale as delta n here. And does this entropy computed in this way agrees with entropy determined by other methods? Like in gravitational theory, there is this walled entropy I told you, which comes from Noether current, and it exactly matches. It was not designed to match that, but it matches. Up to this point, I have been honestly following the philosophy of top down. Start from classical gravity and then try to tell you something. But at this stage, you get ambitious. If this is really true, in the case of gas, what we will do is that we will use the suitable thermodynamic extremum principle, right? And from that extremum principle, you can obtain the dynamics of this system. So you need some suitable thermodynamic potential, and you do that. So now I ask a bottom-up kind of a question, not very bottom-up, but at least sort of from first floor up kind of a question. Is there an extremum principle, and can I write down some kind of a thermodynamic potential from which I can obtain the gravitational dynamics of this system? So here I am sort of deviating from the philosophy and speculating a little bit further. You have gone up to this, so this looks like the most natural thing. Take what this system is telling you very seriously and ask for a completely thermodynamic description of gravitational theories. So what does it involve? So you need some kind of a thermodynamic potential. What you use depends on the context, even in normal condensed matter physics. It could be entropy, it could be free energy, it could be enthalpy, which should connect the fundamental and the emergent description in terms of some suitable variables. Both the variables which you use, the independent variables which you vary in your lab, as well as the form of this, is going to depend on the, in the laboratory system, it will depend on the system. Here it will depend on the class of observers, because the whole thing is now observer dependent, even the temperature to a horizon is observer dependent. But you want finally the equations of motion for the space-time evolution to be independent of any of the observer. So we need some suitable thermodynamical potential, some function of QA, extremizing which for all class of observers should give me the field equations. So how do I go about that? So let me try to describe the logic behind it. The mathematics is fairly straightforward but technical, but let me try to describe the conceptual logic. So you start from principle of equivalence, which essentially tell you that all gravitational theories has a metric description. Then you take any given event. Around that event there are local inertial frames, but more importantly around that event there are also accelerated observers, which are local Rindler frames, which has a local horizon and a temperature. So geometrically this is how it looks like. This is a space-time in arbitrary coordinate. These are the null rays which are going through this point in some arbitrary coordinate. When you go to the local inertial frame, these rays become 45 degrees. These null rays become 45 degrees in that coordinate system. And then there is a region of validity of this local inertial frame, which is determined by the curvature radius of the background. Now you choose the Rindler observer to straddle this horizon so that he can live well within this local region for a reasonable period of time, 1 over kappa time, which you need. Now in the Euclidean picture it is very clear. This circle here tells you the region of validity of the local inertial frame, and a local Rindler observer will have a circle. The hyperbola becomes circle in the Rindler frame, and you keep the radius of the circle sufficiently small. So you can talk about these things in a meaningful way in a local form. Then you ask, suppose there is some flow of matter across the local hot horizon, and it is the old Wheeler trick of throwing a hot cup of tea across the horizon. Will these local observers panic, and will they lose the second law of thermodynamics? Now it seems it is better not to think in terms of throwing tea across the horizon, but instead you can think of a virtual displacement of the horizon. If I push the horizon by this amount, and it hides this particular thing, will these observers lose this thing? Yes, but the way to avoid this is to say that the virtual displacement of a null surface should cause certain amount of gravitational entropy. This is exactly what the message came through in all the previous analysis I told you. And XA going to XA plus QA of X applied to a null surface is like the deformations of the null surfaces. A deformation of the space-time solid by and large does nothing for you, except when you tinker with the null surfaces, because null surfaces encode for you regions of accessibility of information. So if you push around a null surface, that should cause certain amount of entropy because you are playing around with information. So you need to write down S gravity, some thermodynamic potential, it could be entropy, and then you want to extremize that thermodynamic potential for all observers, and that should give you the field equation. So this is the philosophy. So it is very nice in the sense that the local inertial frames tell you kinematics of gravity, how gravity affects the material fields, and the local Rindler frame tells you the dynamics of gravity once you have this thermodynamic approach. So how do you do this? And so here is the pictorial way of representing the same thing. The local inertial frames is what in which you say that all these laws of special relativity should be valid. That gives you the kinematics. You say that in the accelerated observers here, the validity of some thermodynamic potentials extremization, that should give you the dynamics. So you can write down such a variational principle. It turns out that what you need is the following. To the virtual displacements of the null surfaces, which are not in the normal direction, which are essentially null vectors. So you take null vectors in the space-time, and to every null vector field in the space-time, you associate a thermodynamic potential, which is quadratic. It has one quadratic term here with a symmetric tensor here, and another quadratic term in the derivative with this PABCD. Right now, these things are just tensor. This is eventually going to become matter energy time momentum tensor. That is why I have called it TAB, but I don't have to assume it at this stage, and from the field equations I can read it out, but there is no big deal in just calling it TAB. Now you want to take the variational principle with this as some kind of a Lagrangian, and you demand that it should hold for all null vectors. That is different from the usual variational principles, where the variational principle will lead to a dynamical equation for that variable which is varied. Here that is not what we are saying. We are saying there is a thermodynamic potential associated with all null surfaces, and if you do the deformations of these null surfaces, it should be simultaneously extremized. It turns out that this is enough to uniquely fix what this P should be, and that P has to be a derivative of a scalar function built on this with respect to array BCD, and its divergence on all the indices should be 0. That reduces it to a previously solved problem. We know that such f should be just the Lovelock Lagrangians, and there is a classical differential geometry problem which has been solved. Given this condition and this is the unique solution. What is crucial here, just for those who are technically oriented, is that this is like a kinetic energy and potential energy kind of a thing, and when you vary this, you will have a term which is the derivative of this with respect to this variation, divergence of that, right? Just see a miracle which happens there. When you do that, you are going to end up getting this P times one of these objects, and you are taking the derivative of that. Since this object is divergence free, this DC goes in, and because it is anti-symmetric in C and D, you end up getting a commutator of two covariant derivatives. Therefore, that can be written in terms of the curvature tensor. There is no second derivatives or any derivatives of this which will appear in the field equation. That is the whole point. So the derivatives just disappear. Rest is straightforward algebra, and you can show that the theory leads to the extremization of that functional leads to a field equations which are these, which are identical to the field equations in Lovelock theory. Okay. So there is this P is that entropy tensor, this is the Riemann curvature tensor, this is that function which you used to define this, except for one undetermined cosmological constant. That has lots of interesting implication, but I won't go into it in this lecture. To the lowest order, for example, suppose we say that I want to choose for P the one which corresponds to Einstein's theory, which is just a determinant tensor, then you end up getting the projection of Einstein's theory into the null surfaces. Okay, and this one can show is equivalent to full Einstein's theory with an arbitrary cosmological constant. So in D is equal to 4, the answer is unique. The thermodynamic variational principle leads to exactly Einstein's theory, but in other D it leads to the Lovelock theories. There also the answer is unique. Now the cosmological constant, I just want to make one comment. If you go back to your original coupling, it had a TAB times an NA/NB, okay, or psi A psi B in this notation, which are null vectors. So if I change TAB to TAB times a constant times GAB, that just goes out of the action. So there is no way the low energy, there is no way you can introduce a cosmological constant into this theory as a parameter in the low energy action. Okay, that changes the character of cosmological constant problem tremendously, but as I said, I am not going to talk about that. Okay. You may ask, well fine, this gets you the Lovelock models, but you said that you only need general covariance and principle of equivalence. But there is a much wider class of models which is available in this case. Can you get them? It turns out you can. It turns out that you have a, this is the term which I use because I said let us just keep the quadratic term of this fine. But you can add other quadratic terms, and if you take this particular potential, then you can get this full theory. Okay, this is much more than Lovelock. So what it is telling you can be stated in the form of a mini theorem. You give me a Lagrangian which depends on the Riemann-Christoffel tensor and the metric, which on variation leads to a field equation. You are varying GAB there. Then I will give you a thermodynamic potential for every null vector field in the space-time. The extremization of this will lead to exactly the same field equation. So all class of these theories which we saw has the internal evidence exhibiting a microscopic structure of space-time and leading to some kind of a thermodynamic description does allow an explicit thermodynamic realization. They can all be studied in terms of some thermodynamic potential. Okay. So far I kept saying thermodynamic, but I didn't give any connection. It was just a functional. You can just call it a Lagrangian for the null vector fields. So where does this connect with the thing which I know? To do that, after you have extremized it and you have found the extremum, you can go and calculate what that quantity is on an on-shell solution. then you find that in the context when you use the entropy as the relevant thermodynamic variable, two things happen. First, the entropy in a given region resides on its boundary. That is again non-trivial, because when you go back and substitute the solutions into that functional, certain terms cancel out and you end up getting a total divergence, so that when you integrate that functional over a space, it gives you the boundary. So the gravity again turns out to be holographic. There is one more non-trivial consistency check. In any solution with the horizon, it gives the correct walled entropy computed by other methods. So this was not designed. So again you find that that is exactly what comes out. And remember that the walled entropy came from a Noether current, and the Noether current itself has some diffeomorphism invariance. And diffeomorphism invariance and the Noether current leading to entropy had no simple explanation in the conventional theory. Here everything ties on, because the diffeomorphism invariance is just the deformation of the null surfaces, and just as you deform an elastic solid and it causes entropy, when you deform the null surfaces it causes you entropy. There is also some semi-classical result in which it will give you an entropy quantization which becomes area quantization in gravity, but I won't go into that. And it nicely connects with the equipartition idea, because the entropy comes out as discrete bits based on what is there. So here is the summary. So the first point is that there is solid internal evidence to suggest that the dynamics of gravity is like the thermodynamic description. And I hope I have convinced you that the classical gravity has so much of structure which has not been explored in this light, which itself reveals that there is something funny going on. Now, the way to explore that is to use the local Rindler observers at any event, who will attribute some amount of entropy to the patch of null surface. Then the principle of equivalence and the local inertial frame, just as it led to the kinematics of gravity, the entropy balance and the local Rindler frame leads to the dynamics of gravity. So I can write down a thermodynamic functional, extremizing which you can, for all vectors, you get the all null vectors, you get the field equations of the theory. So this is a completely alternate description where GAB is not a dynamical variable, you don't vary metric, you don't have to worry about boundary conditions on the metric, any of those things. It is a completely different way of looking at the same thing. This deep connection between gravity and thermodynamics, which was originally noticed in Einstein's theory, goes well beyond Einstein's theory. This is why I told you right at the beginning that A, you have to think beyond Einstein's equation, because the thermodynamics is telling you something much more fundamental. Second, the moment you go beyond Einstein's theory, entropy is not proportional to area. Entropy is a much more complicated function given by the entropy tensors integral. So if you have ideas which are based on the fact that entropy is proportional to area, maybe that is not the whole story. It may be the story for Einstein's theory, but you may want to think a lot more in lot more detail. So what are the open questions and future direction? Well, one sufficiently cynical attitude which you can take is that, okay, that is all very nice, so what? Now where does it take us further? You have told us that there is some microscopic degrees of freedom, but the whole game is to find what these microscopic degrees of freedom are and to do something further. So what are the atoms of space-time? But this is somewhat like asking Boltzmann to say, get the Schrodinger equation now that you have told me that hydrogen gas has microscopic degrees of freedom. And it is not a inductive approach, so you do need to think along those lines and come up with something imaginative. Second, there is also this question that usually you would have expected all these things to play a role only at some Planck scales or something. But in some sense, null surfaces and horizons act as a magnifying glass for these microscopic degrees of freedom, and they come alive. Mathematically, I know the answer. This has to do with the coordinate dependent infinite redshift that scales to very high energies. But physically, it would be nice to know why this happens, which I don't know. It also brings in a completely new level of observer dependence into thermodynamic variables like entropy of a glass of water. Let me explain what it is. A glass of water is a highly excited state of the inertial vacuum. A Rindler observer looking at the inertial vacuum will attribute to it a temperature. So a Rindler observer looking at a glass of water will attribute to it a different temperature compared to you will attribute to it as an inertial observer. You calculate any thermodynamical variable, these observer dependence will carry through. This result has not been emphasized. There is a new class of observer dependence which is coming into entire thermodynamics, not just for some esoteric quantum field theory in curved spacetime. This is important because if you take a glass of milk and chuck it into a horizon, it is the entropy of this milk and the entropy of the horizon which are going to work together to provide you with a generalized second law. So we need to take this seriously and think about its broader implication. Then there are other issues, like if you know the equilibrium thermodynamics, you can also say a few things about fluctuations around the equilibrium. This was another deep lesson from Einstein. And can we do that in this case? It turns out that there are some interesting things which comes out in the context of entanglement, entropy, etc., but much more remains to be done. Of course, the really ambitious project would be, can one do better than other quantum gravity candidate models? For example, can one say something about cosmological constant problem? Yes, you can, but you can't quite solve it. If the cosmological constant were strictly 0, this provides a very natural interpretation for that. But if there is a small cosmological constant, it evidently comes from some fluctuations around the symmetry getting broken, but one has to actually compute that, which I don't know how to do. Then, for example, what happens near a singularity? Obviously, the thermodynamic description in some sense will break down. Can we say something better than that? Now, so I believe I have convinced you that this is the right way to look at gravity, and with such an intelligent audience, I don't think you will go for a second opinion. But in case you do, these are the questions you need to come up with answers for. How come a current related to diffeomorphism invariance has anything to do with a thermodynamical variable like entropy? In my approach, the answer is simple. When you are doing this diffeomorphism, you are stretching and straining the space-time solid. Normally, it doesn't affect anything. Null surface, you do that, you are tinkering with information. Information is related to entropy. Second, why do Einstein's equation reduce to a thermodynamic identity on the horizon? And why is it that this happens for a much wider class of theories? Why is it that Einstein-Hilbert action has peculiar features? How come it is holographic with a surface and bulk term? Why does it have a thermodynamic interpretation? And why is it that the surface term which you threw away originally does contain information about the entropy of an on-shell solution which you obtain from the bulk? Okay. How come the equations can be reduced to a form which looks so exactly similar to the equipartition law, allowing you to read off the number of microscopic degrees of freedom? This is exactly Avogadro's number for the space-time, just as Boltzmann gave you the Avogadro's number for a gas. How come this works? And how is it that there is some other thermodynamical variational principle which may not be the whole story, it may be a part of the puzzle, which leads to gravitational field equations in such a wide class of theories? Why does such an alternate description possible? So all this fits in very nicely in this approach, and none of which has answers in the conventional approach. And most of this is classical gravity. I mean, classical gravity which you and I have learned for several years now. With that, I will close, and this is just some references in case you want to read this further. And here is a series of acknowledgements. In black are the ex-students of mine in IUCAA. This is a current student of mine at IUCAA. He has been collaborating with me in this work. Ayan Mukhopadhyaya did a paper with me. He is Rajesh Gopakumar's student at HRI, ex-student. Asim Paranchpai is an ex-student of TP Singh at TIFA. We were also collaborating on this. And Donald Lindenwell is at Institute of Astronomy, Cambridge. Apurva Patel is at IISc, and Kandu is with me in IUCAA. And I have benefited from discussions from these people tremendously. Thank you very much.
Thank you for this fascinating exposition. Questions? I'm sure there are many. Bal, please.
I have one question and one comment. First question is, how do you vary R without varying G?
Okay, what is the comment?
How do you vary R?
No, I'm waiting for your comment as well, and then I will answer the question.
For example, if I take any gauge theory, say electrodynamics, the charge is given by a surface integral. In gravity, all the observables are given by surface integral. All the, for example, Poincare generators are given by surface integrals. So, in the sense that you are talking, I can say that the degrees of freedom associated to energy lives on a surface, on the boundary surface. So I don't, it looks to me similar what you're saying, that it's the Witten Nestor form, there's a surface integral. Okay? ADM energy is a surface, angular momentum is a, it is a characteristic of gauge series. Okay?
Yeah.
So what is special here?
Okay. So second part is very easy. What is special is that there is no guarantee that the surface integral can be written in the form of a integration over a temperature times some degrees of freedom, both of which has independent verifiable explanation. So I have toyed around quite a bit with Yang-Mills field theories to see whether any of these carry over for that, okay, whether you can have an alternate principles, etc. None of them work. And the basic reason is that there is no analog of Unruh Davis temperature for those theories, and that is the crucial thing. So coming back to the first one, that is purely a technical issue. The way one does this, one doesn't vary R without varying GAB, one only varies GAB. But when you vary GAB, the result which you get is more easily expressible in terms of a tensor, which is obtained by just differentiating it with respect to RAB.
But how do you get a fourth rank?
Well, this is the Landau's notation, that the derivative with respect to a tensorial object should be interpreted as that quantity which in the Cartesian coordinates is component derivative. So think of it purely as a notation. Okay? So it is not that you are varying it with respect to it. It is a standard notation in Lovelock theory, that they just write P A B C D as dl by dRA.
I had a question and a comment. The question was, you seem to imply that the collection of null surfaces within the space-time seem to contain an enormous amount of...
in fact, they are the only ones to watch out for. Yeah.
I see.
Yeah.
So the question then I had was, you see, what is the special feature in your, you already said it probably, you know, somewhere during your talk, but the horizons, the event horizons and an arbitrary null surface, what is the key, you know, sort of a difference in the two? Sort of
It turns out that in my approach there is no difference. And the reason is the following. Of course, we all know that if you have a nice short sail black hole, the event horizon can be given a completely geometrical interpretation in the Penrose diagram. But we also know that you will know whether there is an event horizon or not only if you live for infinite amount of time. It is non-teleological or whatever, right? I mean, you need to know the full history. So that makes me, like many other people, vaguely uncomfortable that physics should be local and it definitely should be causal, and fundamental features of physics should not depend on the future evolution of the system. So in some sense, I would reinterpret the event horizon operationally. So take short sail metric. In short sail, assume that a black hole has formed, etc., etc., the way anyone would define it. Now you consider two observers, one observer who decides to stay outside, the other observer who is freely falling. It is fairly straightforward to compute what each will observe in a quantum field theory context, and you will find that they observe completely different things. The thermodynamic principles we normally attribute to black hole, which people do not emphasize, but it is observer dependent, because the observers who are freely falling sees virtually no Hawking radiation, and they will not attribute a temperature. So once you take that point into account, all null surfaces and all horizons become in some sense observer dependent. Of course, there is a curvature in one case, there is no curvature in another, but they are not so important. Yeah.
Okay, the comment I had was just this much, that it may not be directly relevant to what you are doing, but in dynamically evolving, you know, situations like collapse or cosmos, Sean Hayward has you know, worked out using apparent horizon and some thermodynamic
most of these,
analogies.
There is this whole lot of horizons, causal horizons, apparent horizon, you know, with various definition. All that I need out of this is a null surface with a null normal in a local patch and some differentiability kind of conditions, which physicists always assume. Yeah.
Sir, I am just a student, so I didn't understand all of your calculations, but just from the essence, can we construct any partition function for gravitation, sort of something like that?
Yeah. The partition function for gravitation in the context of a on-shell solution, like a black hole solution, has been constructed by several people. There is a classic work by Gibbons and Hawking in which in fact, I think the title itself says partition function in some context. So that can be done. The important difference in what I am trying to emphasize is that virtually everyone else who has done this has used metric as a variable. So the partition functions or the thermodynamic variables or free energy or all of them was done with the independent variable being the metric, which is the dynamical variable. What I am trying to suggest is that the metric in the fundamental analysis will be like a density or velocity field of a fluid. It is not like the atomic degrees of freedom. The atomic degrees of freedom, I have no idea what they are, but they are going to be more closely related to the virtual fluctuations of the null surfaces. Okay? I have not been able to connect this with any microscopic degrees of freedom in either string theory or loop quantum gravity or whatever. At some level, the bottom up work has to sort of synergize with what I am trying to do, and that will enrich both of them. But I have not been able to do that. So the main difference between the partition function here and the partition function there is that I am not using metric as a variable.
Okay. First, actually, I don't have comments.
You have several questions.
One is, I suppose this is not dependent on any dimension.
No, it is arbitrary d dimension.
So how do we understand in 2+1 dimensional case there are no black holes?
Let me take it back. It depends on d dimensions with d greater than 4.
Okay.
Yeah.
Okay.
Because it is simple. Mathematically, there is a determinant tensor, and its antisymmetry decides what is the minimum dimension you need.
Okay.
So 4 and above, 1 plus 3 and above.
Then what about the horizons like extremal black holes?
Okay. Horizons like extremal black hole, to the extent they are null surfaces, poses absolutely no problem.
But walled entropy will have some...
Yeah, that will have a problem, and my talk was a khichdi, as you would have noticed. So there is the first part of the talk where I start from the known classical equations and try to convince you that it has a thermodynamic underpinning. That will not work for extremal black holes because there is no T which you can define. T will go to 0, right? But there will be an entropy. So I do not know how to handle it. But the other aspect which I described to you, where you have a null surface, you have a thermodynamic functional, and you vary it and get it. It doesn't care whether it's an extremal black hole or a non-extremal black hole.
Okay. The last part is you essentially look like Minkowski and Rindler space, which is being compared.
Breaking the translation invariance because I have to take a local event. At that event, I have a local inertial frame. Then I have a local Rindler frame. For every event, I have to play this game. So there is no translation invariance in my background space-time anyway. It's like an inhomogeneous solid whose elasticity I am studying. Right.
When you use metric, you have to integrate over the metric modulo diffeomorphism. Since you are replacing metric by a kind of a null vector, do you have an analog of that in your formalism?
Yes, but that analog turns out to be rather trivial, because if ni is a null vector, f of x ni is also a null vector, and there is no unique normalization for null vectors. So you have to do modulo that, but it turns out that it is absolutely trivial to do that. Yeah.
Thank you. We'll continue this over tea.